Well, this little short section of notes is about electrolytes and how we deal with electrolytes in molarity. You've probably heard the word electrolytes before, and maybe you drink a sports drink like Gatorade or something that promises to restore your electrolytes or give you electrolytes. But you maybe have wondered, what are these things? Well, we're going to define what electrolytes are, and you may be surprised at the sort of things that make electrolytes. We can say that electrolytes are solutes that yield electrically conducting solutions. That's what an electrolyte is, something that when you dissolve it in water, it conducts electricity. Now, for electricity to be conducted, two things have to be true. One, you have to have charged particles. That's what electricity is. Electrical current is moving charged particles. Ions are charged particles. The other thing that has to be true is the charged particles have to be able to move from one place to another because electrical current is moving charged particles. So a clump of salt, even though it has ions in it, doesn't conduct electricity. But a clump of salt is an electrolyte because when you dissolve it, the particles are now free to move, and that makes it an electrically conducting solution. So a condition for a substance to be an electrolyte is it has to either be able to produce or contain itself charged particles. Two things primarily can do this. One kind of electrolyte is ionic compounds or salts. Ionic compounds that will dissolve in water, insoluble ones don't do anything. They dissociate in water to release their individual ions. So the ions are already there in an ionic compound, in a salt. When they dissolve, they just dissociate. The ionic compound gets taken apart and the individual ions are released as individual particles in solution. One example would be sodium chloride. When solid sodium chloride is put in water, the crystal tears apart and I get individual sodium ions, which are positively charged, and chloride ions, which are negatively charged. Because these are charged particles and they're now separate from each other and exist in aqueous solution, well, that means that this is an electrolyte. Another example would be sodium sulfate. If I take sodium sulfate apart, when I dissolve it, two sodium ions are released. They're now free to move in aqueous solution, and a sulfate ion, SO4 2-, is released. So this gives three particles for every formula unit of sodium sulfate, and they're charged. So there are moving charged particles present in solution. A second substance that can function as an electrolyte is a molecule, but there are only 6 of them. These 6 molecules are acids, and they're called the strong acids. They don't have ions in them. Molecules aren't ionic, but they undergo something called ionization in water. So a chemical reaction actually happens with water to produce ions. Hydrochloric acid is a famous strong acid. It's present in your stomach, among other places. Hydrochloric acid, when it goes into water, actually does this. Hydrochloric acid will react with water, H2O, and it will actually donate its proton to water to form something called the hydronium ion, H3O1+. And with the proton, with the H taken away from hydrochloric acid, you end up with the Cl- ion. That's the reaction that produces ions. Most of the time, I'm going to model this a different way. I'm going to take the water out, and I'm just going to say H plus Cl-. So here's the ionization reaction, as I would write it, for hydrochloric acid, H plus Cl-. Now I've got aqueous ions. They weren't there before. It was just a neutral molecule. Now I have aqueous ions in solution, so that makes it an electrolyte. Another famous strong acid is sulfuric acid, H2SO4. You notice that there's a subscript 2 behind the H, so what's going to happen when this ionizes is I'll get 2 H plus ions, and I'll get an SO4 2- ion. These are aqueous ions in solution. They didn't exist before, now they do. So that strong acid is an electrolyte. Here's the complete list of the 6 strong acids that we consider completely ionizing. There are many, many other acids, but they aren't strong acids, so they're not considered electrolytes. Perchloric acid is HClO4. When an acid's name ends in ic, that means it's made from the ion that ends in ate. That sounds like it. So perchlorate, which is ClO4 1-, as an acid is perchloric acid. Hydrochloric acid we've already seen, HCl. If it starts in hydro and ends in ic, then that means it's a binary acid. It's only made from hydrogen and one other element, in this case chlorine. Hydrobromic is going to be another binary, so that's HBr. Hydriodic is HI, another binary. Nitric acid, well, that ic ending says nitrate, so that's HNO3. You can recognize the nitrate, NO3 ion there. And sulfuric acid, sulfate ion. And we've seen this formula already, H2SO4. Those are the strong acids. Molarity is affected by electrolytes in the following way. If you think about a molecular compound dissolving, the molecules in the solid remain intact even after the compound has dissolved. Sugar would be an example. If I put a sugar cube in water and let it dissolve, here's my sugar cube here, as the individual molecules of sugar are torn away from each other in this crystal and disappear into the solution, the sugar molecule remains intact. There's a sugar molecule there. It's surrounded by waters. It makes that water shield that we learned about in the last set of notes. But the sugar molecule is still a neutral sugar molecule, so it's not an electrolyte. And if I have 5 moles of sugar dissolved in this water, I'm going to have 5 moles of sugar molecules, 5 moles of particles. But when an electrolyte dissolves, multiple ions are released for each molecule or for each formula unit. So for example, looking at sodium chloride crystal here, the sodiums are the little red spheres and the chlorines are the big blue spheres. The water molecules tear them apart and surround them to make these shields. But now, for every formula unit of NaCl, I have 2 particles, 1 sodium ion and 1 chloride ion. So if I put 5 moles of sodium chloride, I don't have 5 moles of particles. I'm instead going to have 10 moles of particles in my solution. So the molarity of the ions is not always the same as the molarity of the formula units. Let's look at some examples. Let's say I had a 2 molar solution of calcium chloride. What would be the concentration of ions? How many particles would be in there? Well, if I look at what happens to calcium chloride when it dissolves, it's an ionic compound and it's soluble, so it's going to split up and it's going to make a calcium 2 plus ion plus 2 chloride ions, 2 Cl minuses. So here's 1 particle, and here are 2 more particles. So if I started out with 2.00 moles per liter of calcium chloride, I will have 2.00 moles of calcium ions per liter, but I'll have 4.00 moles of chloride ions per liter. So the total molarity of particles would be 6 moles per liter. There would be 6 moles of particles per liter. A way that we express concentration in a sort of a shorthand is put square brackets around an ion. So that square brackets around calcium ion means concentration of calcium ion equals 2 molar. Concentration of chloride ion equals 4 molar in the solution. And we'll use that shorthand the rest of the time here. Another question, what's the concentration of all ions in a 0.01 molar Al2SO4 solution? You give this one a try once. Stop the video and try and piece out what's the concentration of aluminum and sulfate. Well, here's your answer. If I look at aluminum sulfate dissociating, I'm starting out with a compound that has 2 aluminums for every 3 sulfates. So that's how it's going to split up. I'll get 2 Al3 plus ions in solution, and I'll get 3 sulfates, 3 SO4 2 minus ions in solution. If I have a 0.01 molar solution of Al2SO4, every one of those gives me 2 aluminum ions. It's a stoichiometry thing, 1 to 2. So 0.01 moles of Al2SO4 give me 0.02 moles of Al3 plus. 1 to 3 ratio for the sulfate, so I would have 0.03 moles per liter sulfate ion. So my concentrations are Al3 plus aluminum ion concentration is 0.02 molar. Concentration of sulfate ion is 0.03 molar. There are more particles when I get done with than when I started with. Here's one that isn't an ionic compound. This is an acid. How many moles of H plus are in 250 milliliters of a 0.153 molar solution of H2SO4? This isn't asking for concentration. It's actually asking how many moles of H plus. We can find out what's happening when H2SO4 undergoes ionization by just splitting it up. Remember, the subscript 2 means I'm going to get 2 H pluses and I'm going to get a sulfate, SO4 2 minus. So if this is a 0.153 molar solution of H2SO4 and my ratio is 1 to 2 for hydrogen ions, the concentration of hydrogen ions in my solution is going to be 2 times 0.153, and that means 0.306 molar. So that's my concentration of H+. Well, the question is really asking me how many moles of H+ would be in 250 milliliters. So I can do this. Starting with 250 milliliters, because my solution is 0.306 moles of H+ per liter, or per 1,000 milliliters, I can now calculate how many moles of H+ will be present in solution, because milliliters are going to cancel, and I'll get moles of H+ when I do my calculation. I should have 3 significant figures. My answer is 0.0765 moles will be present in that fourth of a liter of solution.